All right. Thank you for the introduction. So, yeah, I'm going to talk about the setoid model. So that's some old stuff, right? This was done by Martin Hoffman in 95 or something like that. And in his PhD thesis, he gave two translations from the calculus of constructions to the calculus of constructions, which interpret every type as a setoid, context as setoids, etc. And crucially, these are syntactic translations, right? So they translate type judgments of the source theory as type judgments of the target theory, and they preserve conversion. And on top of that, they validate the usual extensionality principles that we ask of extensional type theory, really. So function extensionality, proposition extensionality, quotient types, etc. Well, okay, there is a bit of a catch because the two models have some downsides. The first model has no true dependent types, and then the second model is missing some definitional equations. So it's enough to prove some equiconsistency results, but it's not quite enough to get a shallow embedding of an observational type theory. So that had to wait for some work by Altenkirch in 99, where basically he adds definitional proof irrelevance in the meta theory, well, in the target theory. So you have this kind of S-prop sort, and then you use that for the equalities of your setoids. And thanks to that, all the manipulations of the equality of they simplify a little bit. You get more definitional equations, and it turns out that this is just enough to get actual dependent types. And then for good measure, in that paper, Altenkirch adds a universe of non-dependent types, and then goes on to say, yeah, probably you can do a full universe using induction recursion. And sure enough, I mean, okay, let's try to do it together. It's not that bad, really. It's a bit scary like that, but you can follow through. So you start with inductive type of code, which will have a code for natural numbers and a code for dependent products. And then for the dependent products, you will define this data type of codes simultaneously with three recursive functions on it. So this element function, this homogeneous equality on the universe, and then this heterogeneous equality on the inhabitants of the types, of the setoids, right? And then for the pi, you ask for a code, then a family of codes, then a proof that this family is extensional. And then for the elements of the natural numbers, they are just the meta-natural numbers. For the elements of function setoids, then there are setoid morphisms. The equality on the universe is, extensional equality for the pi's. It ignores the extensional component, so you don't have to care about it. And likewise for functions. Okay, yeah, it's not that bad, really. But is this actually a definition? I mean, Agda accepts it, so it must be, right? Well, actually, if you look at it a bit closer, you realize that this is a bit of a sketchy case. It's like double induction recursion, where you have this part here has like two arguments instead of one. So it does not really fit in the frameworks that have been done somewhat properly. So you might feel a bit uneasy about that. But fortunately, actually, this problem has been solved too. So there's a more recent paper by plenty of people, Altenkirch, Pujet, Capuzzi, Sattler, and Sestini. And then they explain that they actually can eliminate this double induction recursion and just use inductive families, or even slightly better, well, depending on your tastes, a plain inductive family in a theory with S-prop valued equality with large elimination. But then it's not that great either, because like nobody really knows or nobody really understands these two theories. Like if you just try to add it to plain Martinov type theory, you could also use OTT instead, but then you're kind of writing a model of OTT inside of OTT. Well, okay, great. The first thing I want to talk about is basically just me hacking in Rock and coming up with a definition that seems to work. I mean, well, it's even formalized, so it actually does work. So let's try to show the gist of it. So here I rewrote the definition from 2 minutes ago, and then I did not write the definition of equalities because we need a bit of space. So, well, the problem is that you would want to use the kind of usual trick to reduce induction recursion to plain induction by noticing that the type in which the inductive part lives is larger than the codomains of the recursive functions. And then you can use the usual trick. But then the problem here is that it's not true because of these equality parts. They prevent you from using that trick. So, okay, well, let's get rid of it. And yeah, but then they also appear here. And then, okay, I don't really want to get rid of that one. So what I will do instead is add an arbitrary equality. I mean, it's just a relation. We don't ask anything on it in the code. And then I can use these here. And then, okay, this thing is now self-contained, right? And there is the technique of small induction recursion that applies. So you can encode this thing as an inductive family and get the same recursion principle and computation rules. But then, it's not really the universe that you wanted, right? Also, a cool thing is that once you have that, you can define setoid equalities on the universe and on elements of the setoids. And you never will actually need these A equal and P equal things. You can just look at the rest of the codes, and that's enough to define the equalities. So then you can do a third step, which is just like writing some family that carves out the codes for which these families A equal and P equal actually correspond retroactively to the equalities that you defined afterwards. So yeah, you kind of do this, and then you define your new universe as just a pair of code in the approximated universe and a proof that it has that thing. And well, okay, it works. It's not that principled, it's just a hack, but okay, you get like a universe with all the nice stuff. And from that, you can actually get a proper syntactic translation of MLTT with FunX, PropX, UIP quotients into just MLTT plus SProp. No fine print. And that preserves conversion. Okay, so that's the first part of the story. Yeah, it's quite nice. And then, okay, I wanted to have a bit more content, so I started thinking about stuff that happens when you try to use setoids. And yeah, when you use setoids, you start introducing a layered system where you have a layer in which you do your computationally relevant stuff and a layer in which you have your equalities, right? And then you have to somehow make these layers interact. Notably, when you want to write quotients, then you should have your equality relation that you want to quotient with live in the same universe as your equalities. And that might involve some truncation stuff. And so this materializes with, for instance, as the fact you have two existential quantifier, you have the sigma type, and then the existential quantifier, which truncates stuff. And then because of that, you will get choice issues, right? Because for the sigma type, you have the usual Martin-Löf type theoretic choice. But then for that existential truncated quantifier, well, you don't, you are not able to go from a relation, you are not able to go from this relation thing to an actual function. So yeah, and that sometimes hinders reasoning a little bit. But actually, this kind of problem is very linked to the sort that you picked for the qualities of your setoids. And you have many choices for that. In Rock, for instance, you have a whole bunch of universes, right? So probably we had talks about these universes a bit earlier in the week, but let me do a quick review of rock universes. So you have S-prop, which is impredicated, definitionally proof relevant, but you are only allowed large elimination for the bottom inductive. All the others you cannot eliminate outside of S-prop. So I just give that one 3 stars out of 5. I mean, it's cool to do some encoding tricks, but then you feel a bit dirty, like you feel like you're doing first order logic, really. I mean, yeah. Then you have the prop universe, the old school, I guess, which is impredicative, morally proof relevant, and then you have large eliminations that are allowed from these things which are called sub-singleton inductive types, and then the 3 big names here are the empty type, the identity type, and the accessibility predicate. So that one I give 3 stars out of 5 also, because, I mean, it's a bit more proof relevant, but it's kind of clunky, right? You are boxed by syntax and you cannot really reason on that. So not that convenient to use. Then you have impredicative set, the weird one. That one you have large elimination for all small inductives, and it allows you to do some weird stuff, but it's even clunkier, so only 2 stars out of 5. And then finally, you have the good old types. Everyone loves them, no restrictions, so 5 stars. Right. And then you can try to do your setoids with all of these variations on universes. So for S-prop setoids, which are the one we talked about just now, you have the problem that once you truncate something, then it's lost for good. You will get no choice at all. So yeah, okay, this might hinder reasoning sometimes. But if you do prop setoids, meaning that you put all your equality relations inside of prop, then you can use this large elimination of accessibility to get outside of prop, and that gives you some bits of choice. Famously, this kind of sigma 0, 1 choice. Okay. Then type valued setoids. These are really nice to play with, because like when you use type, your truncation operation barely does anything. You simply change the equality relation that you had on your setoid to the trivial one, which is always true. And so this allows us to have quite a bunch of cool choice principles. In particular, we have the unique choice, which allows you to say that functional relations are the same thing as functions. Then you have countable and dependent choice for free, because, well, the setoid equality on the natural numbers, this coincides with the meta equality. And so that means that every function out of the setoid of natural numbers is automatically a setoid morphism, and that allows you to have countable choice. Very cool. And then you can even have some, well, with some tricks, you can have some choice for higher order types. For instance, you would want to do the same thing for nat arrow nat instead of just nat. But then you have a problem because you want the setoid equality on that type to coincide with the meta equality. But then for that, we need function extensionality in the meta. Well, what a coincidence. We have a translation that just does that. So if we do this type valued setoid inside of the S-prop valued setoid model, then these have choice for all Martinov types, which are like the types which do not include quotients or propositions. Very cool. And this mirrors some classical results by Hatien saying who does the same thing basically in CZF. He explains that you can actually in CZF interpret these choice principles for all Martinov types. And then what about impredicative sets? You would ask, I don't know, I haven't checked it, so it's just weird. It seems to sit somewhere in between the prop valued and type valued setoids, but well, okay. I don't care enough to check. Okay, so now, well, it turns out that the universe construction of earlier, that one does not care too much where you put your equalities. You can just take that definition, then you substitute the S-prop for your favorite universe, and it just works. Cool. And then when I realized that, I started getting kind of excited. Oh, wow, can we actually get the ultimate setoid translation out of this? And then I talked to Ambrouche about it, and he told me, well, no, actually, these kind of setoids have already been considered by Thierry Coquan, Bruno Barra, Simon Huber. And then they realized that when you try to do this kind of setoid definitions with your proof-relevant equalities, you have the problem that substitutions don't play very nicely with binders. So you have, if you try to substitute sigma in lambda x dot t, then you don't get definitionally, only propositionally, that you have lambda x dot t substituted with the lifted substitution. So you don't really have a syntactic model of MLTT. You have a syntactic model of MLTT minus, which is, MLTT minus this rule. Actually, this was one of the, in one of the earlier papers of Martin-Leff, he actually introduced this theory, which does not have substitution and the binders. So functions are really some kind of black box thing. They're just like, you can put stuff in and put stuff out, but you have very little control on how they are definitionally equal to anything. Okay, this is basically the end of what I had to say. And two questions. Can we derive a systematic encoding of some fragment of double induction recursion from this hack? Might be worth looking into. And then can we find a nice-ish syntax for the proof-relevant observational type theory that is validated by all the models with various universes? Might be interesting too. Thank you.